So you can see that we have this component already there. In addition, we have addition component. So it would be plus epsilon naught into, so epsilon naught is a constant, into rate of change of electric flux, that is d phi over dt. So that is d phi over dt. So that is our electric flux multiplied by with the constant epsilon naught. So it's basically this equation states that the circulation of the magnetic field around the closed loop. So whatever the magnetic field we get here around this closed loop is proportional to two components. First, to the sum of electric current passing through the loop, which is this component multiplied by mu naught, and the rate of change of electric flux, which is this component through the loop. So whatever the changing flux is happening here, that is d phi by dt, and the electric current is going inside the loop, is passing through the loop. So these two components makes up or produces a magnetic field. And that magnetic field is also going to be alternating in nature because you have an alternating electric flux. So it's basically Maxwell modifies the Ampère circuital law by which it takes into account the contribution of the time varying electric fields or electric flux, okay, to the magnetic field circulation. So Maxwell just said that, okay, Ampere's circuital law tells us that this is the equation, but Maxwell tells us that add one more component when you have a change in electric field lines that also contributes to the magnetic field lines production. Okay, and other parameters I have explained in the previous slide. So the new parameters is here. Epsilon naught is the permittivity of free space, is basically a constant that is relating the electric field to the charge density, and rate of change of electric flux d phi over dt represents the rate of change of electric flux through the loop with respect to time, through the loop, this loop that we are talking about. Okay, so the final slide, we have understood the fourth and final equation, that is Ampere's Maxwell law, and we have seen its integral form. Now it's time to take a look at differential form. So again, we are having this figure. We have this alternating electric field applied across the 2 points of this network, due to which we have a changing time varying current that goes in and that comes out of this solenoid shown in the gray curve, due to which the magnetic field lines shown in the blue gets produced, and we have to calculate around this loop, around this integral path. We have to integrate the magnetic field lines to understand their magnitude and their strength. So in differential form, we express this del cross B, that is the divergence. Del indicates the divergence, cross or the curl we have seen in the with the right hand rule. Cross indicates the curl or cross product. So divergence of the magnetic field, that equals to mu naught times J. J is the current density. J is the current density, that is I over A. I is the current and per unit area A. Okay, so it is like ampere or meter square. That is the unit of these current density, and that equals to this first component, and the second component is mu naught times epsilon naught multiplied by the rate of change of electric field. Okay, so this equation is relating the curl del cross B of the magnetic field to the current density J and the rate of change of electric field E with respect to time. And mu naught is the permeability of the free space, and epsilon naught is the permittivity of the free space. So that's all to understand this equation. So we have explained 4 equations of Maxwell's, and we will understand how these things work. We have comprehensively understood how these things work.